Sorry about that. Slope erosion protection, concentrated flow, interface shear strength, and then some not so basic, but probably still familiar to those that have been working with geosynthetics for the past several years. We want to talk about wind uplift, landfill gas pressure relief, traffic, ultraviolet longevity, and then fire resistance. So we're going to touch on all of those in this webinar series, which is going to be a two-part series. The first of which is today, and we're going to start off by talking about infiltration equivalence, which is something required in subtitle D. I'm going to touch on the help model, and then something I'm calling the Giroux model or Giroux equations for infiltration equivalence. Hydrology and hydraulic design, sheet flow design, concentrated flow design with HydroTurf, peak flow attenuation using energy dissipation structures, on-site check dams, outlet improvements to the retention basin, and so on. And then we'll go into shear strength design, static for maximum allowable slope, and then a little bit into seismic veneer deformation, or is it global stability. And then finally, wind design. We'll touch on stability, field wind stability. That's wind shear force versus uplift forces, and then slope hinge stability as well. And then geographic considerations for wind design. The Part 2 webinar, in about a month from now, will touch on these topics: landfill gas relief, traffic, longevity, and fire resistance. I was going to try to get all of this into one session, but to stay within everyone's lunch hour and not interfere with billable time, I was going to have to break it up into two parts so as not to shortchange any of these topics. So Part 2 next month sometime. We'll notify you when that'll be. So first, let's go into ClosureTurf. What is it? It's a geosynthetic final cover system, except for the sand, which is used to ballast down the HDPE grass, engineered turf, and also protect the system from UV exposure. It initially came in a flavor using 50 to 60 mil linear low, or perhaps high density polyethylene supergrip net. Supergrip net has the built-in drainage component that we call the integrated drainage system, or IDS. This is the supergrip net here. You can also use our Giroux microspike product on flatter slopes, which we'll get to in a bit. There's a two-layer woven geotextile that's been engineered for this application. There's two layers in here for dimensional stability. And there's a well-graded sand infill, or hydro binder for HydroTurf, that goes into the synthetic grass or high-density polyethylene yarn that you see here and here. The turf comes typically in green, but you can get it with tan, or in tan with UV stability. So that's available in the drier parts of the country, such as the Southwest United States, Wyoming, and so forth. If you want, you can get it in Idaho State Blue. But know that this color does not come with the UV protection package. That's sold separately. It comes in two flavors. There's what I call the IDS base, which is for side slopes, and that's the engineered turf here, and then the half-inch sand infill over the supergrip net geomembrane with the IDS stud sides up, and then the grips on the bottom for veneer stability against the intermediate soil cover. And then there's microspike based, which is usable up on top decks, shallow slope applications, 5% or so. This is again engineered turf, something we're calling armor fill, and then all that over microspike geomembrane. Armor fill has a polymer mix in with the sand to increase its stormwater flow resistance or hydraulic shear resistance to minimize sand movement over very long stretches, such as would be encountered with a CCR impoundment closure. And then ClosureTurf, what it ain't. It is not an exposed geomembrane. The geomembrane component is fully covered by the engineered turf and sand ballast. There is no exposure to the geomembrane portion itself, thus it's a Subtitle D compliant final cover system. It's been approved all over the United States. Each state has its own approval process, so if you're first in your state, you'll have to go through that approval process, but there's lots of documentation available. So that's as far as exposed geomembrane. ClosureTurf is not an exposed geomembrane. So we'll get started into the meat of the topic here, infiltration equivalence. First, a little bit about the HELP model. HELP model has been around since the earth has cooled, basically. I remember first starting out in the business, you were pretty cool if you knew how to use the HELP model. It's been around for a long, long time. There are problems with it, though. Mostly the underlying equation, the McEnroe equation, is valid only in unconfined flow conditions. So if the flow in the drainage media, be that a gravel layer or a geocomposite or what have you, if the flow in that layer rises up to the top and confined flow conditions start, the model breaks down. So another simulation run would have to be done using a thicker or more permeable drainage layer. So you really can't model hydraulic head on the liner in this situation for a plugged geomembrane. Second, HELP model uses daily average weather data. That would grossly underestimate the actual impingement rate in a peak rainfall intensity, say a 5-minute intensity, and hence that underestimates the head that can form on the liner and can result in undersized drainage systems. Now that problem can be adjusted by inserting custom rainfall data, say 5-minute intensities. But the first, not so much as far as leakage rate in a plugged drainage layer scenario. Third, the freeware version is DOS. That's still available from the U.S. Corps of Engineers. However, my Windows platform anyway wouldn't even open the installation file. I had no idea what that DOS file was, wouldn't even touch it. I did find a Windows version out there, but it's not supported above the XP 32-bit platform, and no technical support was offered. So I could have dropped $1,000 on that software package and been basically on my own. And then finally, HELP is not really well suited for ClosureTurf. ClosureTurf involves a lot of interrelated drainage layer or flow in the drainage layer and in the sand, ballast sand flow, and then surface flow, which you really can't model in HELP. So as an alternative, we have something that I'm calling the Giroux model. This is an infiltration model that was developed by J.P. Giroux, T.D. King, T.R. Sanglerat. I know I butchered his name. I'm not even going to try that name. And then M.B. Curie. This is available on the web at the Geosynthetics Archives or Geosynthetic Society Archives. So you can go to this website here, and they've got a whole host of these papers. Here's this paper that I'm referencing here. It has lots of really cool nerdy equations, including this one, which is what I've got here. So this equation, where Q is equal to the flow through the liner, C sub QO is a contact quality factor, which is basically if you've got a decent construction quality assurance program, this number is on the low side. If you don't have CQA, this number is going to be on the high side, so will increase the flow through the liner. H is the hydraulic head on the liner. T is the thickness of soil beneath the liner. D is the diameter of the liner flaw. And then K is the permeability of that soil layer beneath the liner. And then there are some restrictions on this equation. The diameter of the liner has to be between these dimensions here. The hydraulic head has to be no more than 3 meters deep, which is not a problem for ClosureTurf. And then the permeability of the soil beneath the liner has to be between these ranges here for this equation to be valid. It's all in metric. I haven't done an English conversion on it, but all these variables here are in metric. Well, the question is, well, how can a drainage layer plug? Well, on the top deck, that's fairly obvious. You get differential settlement, you get pools forming up there, you will have a saturated drainage layer. On side slopes, it's also because of settlement, just not differential settlement. As the landfill settles up to 25% of its original thickness, you'll see that the vertical component here is going to shorten while this horizontal component does not. So what you're getting in essence is the hypotenuse of this triangle, or the slope length, is shortening. And all that liner and drainage layer has to go somewhere, so it'll start to bunch up into that overlying soil layer and create these mini dams within the cover system, which then creates saturated conditions and higher hydraulic head on the liner than you would normally expect. Well, let's go through an example of the Giroux model here. First is prescriptive cover versus ClosureTurf on poor soil. So this is a spreadsheet of that Giroux equation here. This is top soil thickness, 24 inches, 1 centimeter diameter hole with the corresponding area of that hole, infiltration layer at 24 inches, and this permeability here, 1 times 10 to the minus 5 centimeters per second, which is the subtitle D standard. And then coefficient for good contact here, 0.21. This is with assuming good CQA practice. If there was no CQA, this number would be 1.15. The upper permeability limit here is where this flow through the liner starts to transition into a Bernoulli flow condition, or this hole becomes basically an orifice. So the permeability of the underlying soil has to be this or greater for you to start getting orifice flow conditions through that hole. So anyway, the estimated flow of this prescriptive cover is 8.7 gallons per acre per day. Over here on the ClosureTurf side, topsoil thickness is 1/2 inch for the sand. Same hole diameters, same infiltration soil layer thickness, same coefficient for contact. Difference here is I'm using this permeability for the underlying soil layer simply to go through the numbers to find a matching infiltration rate to the prescriptive cover. Something about that soil type is it's a sand gravel mix. This is a commodity product. This is not something you're going to find as an intermediate cover on a landfill, this is going to be available in quarries for sale. So we'll go to example 2, which is prescriptive cover versus ClosureTurf with prescriptive soil conditions. Or I'm using this permeability here, the same as with the prescriptive cover, simply because this permeability is your basic dirt. This is a sandy, clayey soil. It's not a pure clay. This is dirt that you're going to find just about anywhere. Having used this underneath the ClosureTurf, the model now says the infiltration is 0.2 gallons per acre per day versus 8.7. So ClosureTurf is as good as or better than the prescriptive standard depending on your soil conditions in the intermediate cover layer or foundation layer. Now what about a sand landfill gas relief layer beneath ClosureTurf? That is an excellent question. However, I'm going to punt it to the part 2 webinar when we talk about landfill gas relief. It is a parameter that you need to be aware of, but there is compromise between the two issues. Next, erosion sheet protection, where ClosureTurf was subjected to sheet flow testing several years ago using this ASTM method. It was a 3-to-1 slope, 40 feet long, and was up to 6.6 inches per hour in intensity. The sediment yield was well below the nominal 2 tons per acre. It does have a curve number of 94 or a corresponding rational method runoff coefficient of 0.76. So pretty much all the water that hits this system is going to flow off of it. We'll get to how to deal with that in a bit. Now, what about longer slopes? That slope that we tested was only 40 feet long because that's the capacity of the system there at TRI. Now, stormwater flow, as I said before, in an SGN-based slope application of ClosureTurf anyway, has these regimes. There's IDS flow here, that's controlled by the IDS matrix transmissivity. There's ballast flow in the sand, controlled by the sand permeability. And then there's surface flow on top of the system, which is controlled by hydraulic shear and open channel flow. This distance here, L sub CR, or the critical distance of the IDS matrix, is determined as the length before the water level rises to the top of the IDS and starts to get into the or saturate the sand layer. L sub S1 is the transition zone where the ballast sand is saturated and it's controlled by the sand permeability. It's very short, it's pretty much negligible. And then L sub S2 is where surface flow begins to develop, and it's controlled by the hydraulic shear capacity of the sand. Now, graphically, we've solved these flow regimes for various slopes and rainfall intensities. Now, pulling an example from one of our previous webinars, top deck conditions, say less than 5% or less, can support very long slopes, as you can see here along this 5% line for typical rainfalls, and then the more intense rainfalls up here, anywhere along this 5% line. For, let's say, a 100-year 5-minute burst, intensity of 6.2 inches per hour, which I pulled from a previous webinar, part 2 on our capping systems series for drainage media design. The allowable slope length at 5% for a ClosureTurf system would be almost 900 feet. Something you will notice that some of these lines are grayed out versus these are black. And the reason being is the grayed out lines were determined mathematically. We have test data up to 6 inches, 6.6 inches per hour specifically, but these numbers here, or these rainfall intensities, were determined mathematically. Now, surface flow is predominant on the top deck of a ClosureTurf system, as shown here. This red line is overland flow, whereas the blue line is drainage layer flow in the IDS matrix. So for shallow slope conditions, it's all surface flow. As you get steeper, the IDS matrix begins to dominate as far as drainage of the system. So we've developed a new version of ClosureTurf that I showed you previously that utilizes microspike up on the top deck situations here, simply because the IDS drainage matrix isn't needed hydraulically in these top deck conditions. Well, let's go through an example. You may recognize this from the Part 2 webinar on shear strength for drainage system design. In that, Q sub n is equal to the permeability of the cover soil times the slope length, or horizontal projection of the slope length. To maintain continuity, K out has to equal K in, thus the horizontal projection of the slope length can be estimated by dividing the allowable flow out of the drainage media by the soil permeability. Case of ClosureTurf, Q sub in equals Q sub out equals permeability of the sand times the critical length of the IDS drainage matrix. Now, I said K sub S is the permeability of the sand, or it can be the permeability of this double woven geotextile base below it, whichever is less. Now for ballast, we use an ASTM C33 sand, which we've measured permeability at this level here, 2.6 times 10 to the minus 2 centimeters per second. And for the geotextile, which was 5 years old from a site in Missouri, permeativity of 0.69 per second. Permeativity is equal to the permeability of the geotextile divided by its thickness. So for a 1.1 millimeter thick double woven geotextile, K sub GT is 7.5 times 10 to the minus 2, which is greater than the sand permeability, so we'll use that. However, that permeability in rainfall intensity units is that. I think if we have rainfall that intense, we're not going to be worried so much as to how a landfill final cover system is going to perform. We'll have bigger problems such as that. Yeah, well, that ain't happening, so not a problem. You aren't going to run into rainfall intensities like this. So anyway, we can determine the critical length from the continuity equation. Now notice here I'm using rainfall intensity versus the sand permeability. This equation is intended for saturated conditions, so I'm kind of stretching its capacity here. But since we're dealing with a mid coarse grain sand, I think it can safely assume that a drop of water that lands here will force another drop out down below here. So ClosureTurf transmissivity testing, 100-hour testing, produced this number for the IDS system, 3.86 times 10 to the minus 3 meters squared per second on a 3-to-1 slope. Applying Reduction factors, creep factor I'm going to use as 1 due to the very low post-closure load, 5 to 10 psf. The IDS system was tested up to 15,000 psf and had a creep factor of 1.14. So I think it's safe to assume it's 1 for this condition. Chemical clogging, reduction factor of 1, since the ballast sand is medium to coarse grain sand. It's not a fine grained material, thus the precipitation of finer grained materials or ions from, say, like a clay soil aren't going to happen, thus the drainage matrix isn't going to get clogged. And then a biological clogging reduction factor of 1, since there's no grass, there's no roots that are going to penetrate into that IDS system. This photo here was taken at the oldest installation of ClosureTurf at the LaSalle Grant landfill outside of Gina, Louisiana. That's been there since 2007, and what they've noticed that along the perimeter of the site, native grasses will try to migrate onto the turf during the wet season when there's abundant rainfall. But as soon as the sun comes out, dries this system out, the grass dies back to the perimeter since there's no water and no food in this system. So biological clogging factor of 1, we'll calculate the corresponding flow rate then as the transmissivity times the gradient, using those numbers and applying conversion factors to get to English units. We have 49 cubic feet per hour per foot of width. Now what about rainfall? Well, I'm going to use that 5-minute burst intensity at 6.2 inches per hour again, and divide the allowable flow rate by that rainfall intensity. Estimates the critical length of the drainage matrix at 95 feet. Now what about L sub S1? Now from another Giroux paper, you can estimate the length when the water flow is parallel to the surface, or right about here, using this equation. Now using 6.2 inches per hour as Q sub H, we can estimate L sub S1 as this, less than an inch. It's negligible. Now for L sub S2, this is dependent on the allowable hydraulic shear of the ballast sand. And we'll base that on the flow depth at the toe of this slope here, or the end of L sub S2, using this equation right out of Chow for hydraulic shear, simply the flow depth times the density of water times the slope of the water flow. So what is the allowable shear? Well, we need to wait a sec on this. For slope applications, it's really difficult to say, namely because we don't have a really long enough slope to really test this in the laboratory anyway. It's also a question of sediment transport, entrainment and transport of the grains themselves, such as in this figure, the particles don't slide over each other, but rather they roll. So you're calculating the moment forces about this pivot point here from the weight of the sand grain versus the fluid forces that are trying to roll it over its neighbor. Now that rolling action is incipient when this moment equilibrium occurs. And this is where the V sub O is the volume of the grain, and then the relative densities of the grain in water, gravity, alpha is the angle from the channel bed to the tangent between the neighboring grains. A sub 1 is the moment arm to the grain center of gravity here, or the weight of the grain. V is the water flow velocity. A is the projected area of grain to flow, and then we've got a coefficient of grain exposure, and then finally A sub 2, the moment arm of drag force on that grain, or this distance here. Yeah, that's a lot of variables. And then these highlighted ones are the only ones you can really know for sure. The rest you have to estimate based on grain size distributions and roughness coefficients of grain particles themselves, etc. And then there's more. For sloping beds, the angle alpha here, you have to replace with alpha minus beta, where beta is the slope angle. So, long way to say, right now we can't really offer you any specific design guidance as far as slope surface water flow other than anecdotal, but there is a case history. This is the Softly Field landfill in Pensacola, Florida. The site was closed in 2013. It was an absolute mess and a royal thorn in the side of Escambia County. Lots of slope failures onto this road, lots of odor and smoke issues from some of the fires that started at this site with these folks living around it. About 6 months after it was closed, it got hammered along with the Pensacola area with a water world level storm that was estimated at having a return period between 200 and 500 years. It was just a brute. From Atlas 14 IDF data, the 5-minute intensity burst for a 200-year event at this site would have been 16.6 inches per hour. It was just a phenomenal amount of water. And even though Pensacola got beat up pretty good by this storm, this site went through it with hardly a scratch. There was basically a 1% sand loss over the entire 23 acres of ClosureTurf cap at this site along these side slopes here, toe of the slopes where there was some sand boiling, and especially along this slope here where some of this overland flow went over the edge and down the side slope here. But again, only a 1% loss due to a storm of this magnitude. So long story short, side slopes with ClosureTurf can take a lot of rainfall. Exactly how much and what design equations you might use, don't know. Can't really tell you at this point. Just that it can take quite the beating. Now, what about top deck conditions? Well, like I said before, it's all surface flow. So we can assume the critical length of the IDS matrix is 0 since you don't have to use it, especially if you're going with microspike. L sub S1 doesn't matter. L sub S2 is a function of hydraulic shear. Now, how can we determine that versus using that crazy sediment transport theory? We did a test for that. Back to TRI, these guys have way too much fun with water. They did a bed slope test up to 10%. Get us these numbers here, Manning's roughness coefficients, and then maximum bed shear stress, along with sand loss, accumulated sand loss throughout the test. That provided this chart from which we're going to try to determine what the maximum allowable sand loss is. Well, to do that, we'll use the typical 2 tons per acre. That's equivalent to 0.092 pounds per square foot. With a sand unit weight of 110 pounds per cubic foot, that implies an allowable sand loss of 0.01 inches. You can't even measure that. If the sand ballast thickness is 0.5 inches, that's a loss of 2%. So I'll plug that 0.01 inch loss into the chart equation here, and back calculate the allowable hydraulic shear is 0.25 pounds per square foot. So now plugging that into our shear equation, I estimate the depth of flow at the end of this length here at little less than an inch. So since the surface flow is basically open channel flow, we can find the length L sub S2 from Manning's equation using this depth of flow as the hydraulic radius. In Manning's equation here, which will give us a critical flow of 433 cubic feet per hour. Plug that in to our equation using the design rainfall intensity, implies the allowable slope length for L sub S2 is 840 feet. Very long, almost 3 football fields long. You can put this stuff on very large sites. And finally, as far as erosion goes, what does stormwater runoff from ClosureTurf look like? Well, this is the Tangipahoa landfill in Louisiana again. And this site had some stormwater issues, multiple cease and desist orders as far as discharge from the site. Stormwater runoff from this site used to look like the jar on the right. It now looks like the jar on the left from the ClosureTurf slopes. I'll let you do the math as to what that implies for the industrial stormwater permit compliance. Needless to say, the site managers at Tangipahoa are very happy that their water doesn't look like this anymore. Concentrated flow. Well, once sheet flow becomes concentrated, you have to replace the sand ballast with a sand cement compound called hydrobinder to create hydroturf. Some more ASTM flow testing was done on this version at a 30% slope. Again, we got some Manning's roughness coefficients here, maximum bed shear stress, and then the cumulative loss of material, of hydrobinder material, which gives us this chart. The testing apparatus was not able to test the product up to its failure point, so we're projecting up to about 20 psf as its maximum hydraulic shear. Minimal ballast loss was measurable at, say, 10 psf of shear strength here, or 0.05 inches of cumulative loss. So plugging that into our shear equation gives us maximum flow depths at slope of these, anywhere from almost a foot to 4 inches. So using those maximum flow depths and then the Manning's roughness coefficients for those depths in Manning's equation gives us this chart here for trapezoidal channels. Anywhere from 12 feet wide to 4 feet wide, you can get these kinds of flows at these slopes. One nice thing about this channel shape is that this can be easily cut with a dozer, especially those with articulating blades where they can shape these berms to the nice side slopes here that you see. These have been installed several locations around the country now, and they work really well. For V-ditches along access roads and benches, got to determine the maximum hydraulic radius allowed at a 10% pounds per square foot shear strength. So for typical V-ditches, 1-to-1, 2-to-1, 3-to-1, here are the maximum allowable flow depths. As you can see here, these flow depths are basically ridiculous. You're never going to get a V-ditch that deep on a bench side slope. So you can make these ditches as deep as they need to be for your design flows. You can consolidate access benches with drainage. If you've got enough cross slope on the bench, you can basically incorporate that cross slope as a drainage media. This is nice because you don't have to cut into this soil layer and potentially expose trash by putting this V-ditch in. I've used this myself. It's a good solution. It's worked quite well. And yes, you don't have to cut that V-ditch in or build up that bench section to allow the cut. Peak flow attenuation. As discussed previously, ClosureTurf has a very high runoff coefficient. That means high and quick peak flow, or something like this chart here. The blue flow is discharge into a sedimentation basin. The red is the flow out of that basin that had to match this pre-landfill flow for low impact development regulation reasons. We had to do some finagling with the outlet to this basin to make this happen, which I'll get to in a bit. There's a couple of methods to control that peak flow. One is on-site detention structures. These are basically sackcrete stacked with openings in here, holds water behind it, but once the rain stops, all this water drains out, thus you're not ponding water on top of a landfill. It was able to increase times of concentration in the individual subbasins up to 5 minutes. So does decrease overall peak flow from the site. Another one, and this is the outlet improvements, is we installed a weir and a sluice gate in order to temporarily increase storage in the basin itself during peak flow. The design relied only on the sluice gate to meter the peak discharge for both the 100-year and the 200-year peak. The client added the siphon that you can see here to drain the pond and restore retention capacity between storms. So there are ways to cope with the higher runoff potential of ClosureTurf. You just got to pull out your engineering cap and come up with their solutions. Shear strength design, turf versus IDS. Well, for maximum allowable slope, there are two conditions. There's construction, and then there's post-closure. And these are peak and residual shear points of turf versus the IDS studs, and then 2-to-1 slope, 2.5-to-1 slope, 3-to-1 slope, all factoring in a factor of safety of 1.5 landing here. You can see 2-to-1 slopes get a little problematic. The lesser slopes should be fine in all conditions. For supergrip net versus soil, again, we've got two conditions. Peak, this is a very complicated chart, but again, we got the 2-to-1, 2.5, 3-to-1 slope curves here. And then green represents the interface shear strength of the grip side of supergrip net versus granular soils. Blue is supergrip net grip side versus cohesive or clay soils. It does better with granular soil types, so much so that the average line formed here is above even the 2-to-1 slope for peak conditions. And then for clay soils, 2-to-1 starts to be a problem. And then we go to residual, 2-to-1 slopes again, kind of okay for granular soils. Lesser slopes, 3-to-1, 2.5-to-1 should be okay for most conditions. One thing I need to point out is these dashed lines here represent what I'm calling the 90th confidence interval. So you run another test of supergrip net grip side versus your soil at your site. You can be 90% confident that it should fall in between these lines here, this line and this line. Your result should land somewhere in between them. For maximum allowable slopes, we'll look at microdrain versus soil. This is actually microspike test versus soil. Again, we're talking peak. 2-to-1 slope lands pretty much along the average of the test results, so kind of problematic. Lesser slopes, 2.5 to 3-to-1, are okay for peak condition. Same holds for residual. 2-to-1 slope is starting to cause issues with residual condition or residual shear strength. 2.5, 3-to-1 should be okay. Wind design. Now, a lot of concern was initially raised by regulators that ClosureTurf was an exposed hybrid geomembrane. Not so. Now, wind can be death for exposed geomembranes. This is known. ClosureTurf does not behave like an exposed geomembrane. Did a strange thing up around here. It peaked and now started to drop. Once it reached Category 1 hurricane wind speeds, it started to go negative as far as uplift goes. And the reason being is you see these grass blades starting to fold over under the wind. Well, that means they're also pushing down on the fabric below. And then you notice this wind flow indicator is pretty turbulent here versus these guys up here. There's a reason, and we'll get to that, or the importance of that in a minute. But first, how do you design with this type of information? Is actually shear governs, not uplift, but shear governs. They measured developed shear force during that wind tunnel test. As you saw, the normal loading was a maximum of 0.1 pounds per square foot. By normal, I mean uplift. But using the wind tunnel data for shear and uplift and applying a factor of safety, we can determine the weight of sand required to hold the whole system in place, where tau is the measured shear force from the wind tunnel. Phi sub turf is the interface shear angle residual between the turf and the IDS studs, and then P is the wind loading normal force. And that produces this chart. Here's edge or hinge conditions, slope hinge conditions, and then interior conditions, all using these parameters here. To calculate the required weight of soil, simply go from your design wind speed here up to the blue curve to determine that you need 10 pounds per square foot along slope hinges. And out in the field, we need about 1.5 pounds, which actually is well below our nominal ballast thickness of 1/2 of an inch thick. So for field conditions, you get the sand applied per specification. You don't really need to worry about movement of the system under a wind. Did the same thing for the microspike configuration here. Along hinge conditions, you need a little bit, you need some more sand ballast thickness here, up just a little more than 14 pounds per square foot. Out in the field, you're still safe with the nominal 1/2 inch thick sand under this wind condition. Now, where is wind design a concern? Well, using ASC 7, this is from the 2005 edition. There's a 2010 out where I think these wind speeds increased a little bit. There could be a 2015 out right now. But my previous example site, the 115 miles per hour, was here, a special wind region of northeastern California. What about here along the eastern and Gulf Coast states that are going to get hit by hurricanes? Well, these higher wind speed effects on exposed geomembrane anyway can be modeled from yet another Giroux technical paper, and another one you can or worked on with J.G. Zornberg. You can estimate the wind suction uplift force along a slope using this equation here, where this parameter lambda is the suction factor along, say, a slope or other geometric shapes. V is the wind velocity, kilometers per hour. Z is the elevation of the site in meters, and then mu sub GM is the density of the geomembrane. Of course, we've got the gravitational constant here, and then the cosine of the slope. However, ClosureTurf doesn't behave like an exposed geomembrane, so that equation is simply not valid. As I said before, the turf creates a turbulent zone right above the grass blades. That breaks the suction force all the way up to Category 3 hurricane wind speeds. Now, above Category 3, Category 4, Category 5, for those of you who might have something along the Gulf or eastern coast of the United States, or right at the coast, you should probably run a higher wind test to see what will happen. Will that pressure force stay negative? Likely up to Category 4 and 5, but we don't really know because we just don't have the data. Now here in the western United States, not such a big deal, other than maybe some special wind zone somewhere within the western United States may get up into those higher wind speeds. So that's today's webinar. Next webinar, next month sometime, we'll let you know when that'll be. We'll talk about landfill gas relief. We'll talk about traffic and longevity, some really cool field data, and then lab testing from the Geosynthetic Research Institute, and fire resistance. So that's next time. For those of you looking for PDH credit, it's available in these states in the western United States. PDH is not required in Colorado, Washington, Hawaii, and go figure, my home state of California, or which may someday be the state of Jefferson, where I happen to be right now. But anyway, if you need PDH credit, give either myself or Nathan Ivy a holler, and we'll get you set up with a cert. And we have some questions forming here. See, let me start at the top here. Okay, that's me. Are you going to send out the presentation? Yes, in PDF form. If you want to have a copy of that, we'll get that to you. Is there any maintenance needed for the synthetic turf? To date, no. We have not had, other than that site in the Softly site in Pensacola, Florida, there's not been any need to replace sand on any of these installations. Has it been used in areas that have freezing rain or snow? Yes, in Pennsylvania, there's a site that a lot of snow, a lot of cold temperatures, such as you've asked here. To my knowledge, that site has not had any issues with freezing rain or snow having impacts on operation or function of the system. We've used it in Chester County, Pennsylvania, both snow freezing conditions in the winter. Good to know. That may be the site I'm thinking of. Maybe we can talk about that later. Please send me info on those applications. We'll get you we will get you a reference to those sites. Can I make you the presenter? No, I really can't make that happen. And yes, we will send certificates for PDH credits. Just send me an email and I'll reply back with a PDH credit. That may happen today, but should definitely happen before the end of the week. And this session was recorded, so it will be available on our YouTube channel just as soon as I process the recording and get it moved over to our website for uploading to YouTube. So anyway, if there are no further questions, we'll sign out here. Again, if you got questions or need a PDH cert, just shoot Nathan or myself an email and we'll get you set up. So again, thanks for tuning in, and we'll see you next month.